Hey AP Statistics, welcome to Chapter 7, Sampling Distributions. This will help us form the foundation of what we'll be doing in the next couple chapters, which when we really get into inference, drawing conclusions from our samples. So we kind of want to know how samples behave, and to understand that, we want to look at sampling distributions. So by the end of this first section, you should be able to distinguish between a parameter and a statistic, create a sampling distribution using all possible samples from a small population, use the sampling distribution of a statistic to evaluate a claim about a parameter, distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution, determine if a statistic is an unbiased estimator of a population parameter, and describe the relationship between sample sizes and the variability of a statistic. So, statistics and parameters. A statistic is a number that describes some characteristic of a sample. A parameter describes some characteristic of a population. So some examples are sample statistics we know are X bar. And so you've seen these guys before, so this shouldn't be brand new, but X bar is a sample mean. The parameter would be the population mean. So if I go out and I get like 50 people and take their mean, that's my X bar, my statistic. But the mean of all the people in the world, or whatever population I'm interested in, that would be mu, the population mean. We've got our sample proportion. This bit is actually newer. So p hat is the symbol we use for sample proportions. We've talked about proportions before, but finally giving them the specific symbols. So the sample statistic for a proportion, when you're dealing with categorical data, what proportion of people, are boys or girls, or favorites colors red or something like that, where it's not quantitative, like with a mean, you can do a proportion. And then the population proportion, we just use p, so that's p hat. Notice there's a little bit of a trend between here where we use like regular letters, maybe with an additional like symbol or thing going with it. Whereas over here, we tend to actually use Greek letters. Some textbooks will actually, instead of using p, they'll use pi for population parameters, because they use like p hat for the sample and then pi for the population proportion. For obvious reasons, that creates some confusion, so we avoid doing that with our textbook. We just use p for the population proportion. And then we have our sample standard deviation S sub x and the population standard deviation sigma. But these aren't the only statistics and parameters. There can be lots of things. You can have other statistics we know is like interquartile range, where you can have a sample interquartile range, and you can have a population interquartile range. You could have a sample version of any kind of numerical summary, and a population version of that as well. So a lot of examples in this one to go through. Identify the population, the parameter, the sample, and the statistic of each of the following settings. So a Gallup poll asked 515 randomly selected U.S. adults if they believed in ghosts. Of the respondents, 160 said yes. So ultimately here we have our population is who we are going to be interested in. So U.S. adults seems to be our population. This 515 is our sample. So our population is U.S. adults. The parameter, we don't actually know, but it would be the proportion of U.S. adults who believe in ghosts. The sample was this 515 U.S. adults, these 515 individuals that were randomly selected. And then our statistic in this case is a proportion. It's a p hat, and it's the proportion who said yes, who actually say that they do believe in ghosts for that first one. For the second one, during the winter months, the temperatures outside of the Starnes' cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperatures at 20 randomly chosen times during a given day. The minimum reading is 28. So in this case, our population is all times during the day in question. So we have a single day of times, or all the times across that day. Kind of a weirder population. How many times are there? This is kind of you can have kind of infinite population sometimes, right? So that's what this one is. It gets these can get a little weird. And then the parameter would be the actual true minimum. So that we're interested in the minimum that it gets to. Where our sample is those 20 randomly selected readings, and then our statistic is that 38, which is that minimum that it got to. So, AP exam tip, many students lose credit on the AP statistics exam when defining parameters because their description refers to the sample instead of the population, or because the description isn't clear about which group of individuals the parameter is describing. So when defining a parameter, we suggest including the word all or true in your description to make it clear that you aren't referring to the sample statistic. I'll be referring back to this. This may not actually make a ton of sense right now, but I'll be referring back to this a lot because, yeah, I've graded the test, and this is something that we look for, is that, yeah, you don't get the two confused. The idea, and this is a big idea going forward, that you don't get your population parameter confused with your statistic. And this is just a big idea in general, that people get this sample and then they'll publish their research and say this proportion of people. Well, that was a statistic. We don't actually know for sure if the population proportion perfectly matches that. So we should purport that, there's some margin of error or something like that relates to that reported statistic. So really, really something that this AP statistics class likes to drive home is understanding the difference between your sample proportion or sample mean and your population proportion or mean. And so just remember the little rule for doing this: S, statistics, go with samples. Statistics come from samples. And P, parameters come from populations. All right, so then another concept you should already have a decent feel for is the concept of sampling variability. And this is the fact that if we take multiple samples, we're not going to always, even of the same size from the same population, we're going to get different results, right? If we're using randomness, which we should be, to select our individuals, if I get the random height of a bunch of individuals at our school and repeat that process over again, I'm not going to always get the same number. There's variability. And so this is an example where they're looking at years or whatever, so you can see they're getting a mean from that. The sampling distribution, so that it's not just that it's variable, but we actually get a distribution. Notice that each of these X bars, this chapter, by the way, gets very hypothetical, where like you would never actually do this unless you were studying sampling variability or something like that. Usually you just get one sample and get one mean. But this is saying, what if we did this over and over and over again and got a bunch of different means? And so they're plotting X bars, basically. So one time they got an average of 2005, another time they got an average of 2010, another time they got an average of this. And so that's all the different X bars, all the different sample means. And so they vary, but not only they vary, they also have shape, center, and spread. They got all the feature of it. And so that's the distribution of values taken by the statistic in all possible samples of the same size from the same population. So the true sampling distribution is all possible samples. This actually is not all possible samples. In theory, you could probably take a lot more samples from any reasonably large population. It's an extraordinarily high number, but that theoretical distribution of possible sample results is something we want to know. So, for example, calculating a sampling distribution here, we're going to have a very tiny population. John and Carol have 4 grown sons, and so we have the 4 grown sons and we have their 4 heights, 71, 75, 72, 68. That is this is really weird, that's our population here. So we're going to get samples of size 2. We're going to pick a random sample of 2 of their sons, and we want to list all the possible samples we could get. So we could have the height of 71 and 75, 71 and 72, 71 and 68, and so on. So we have all those possible combinations listed. Those are all the possible samples. Then calculate the mean of each of those. We're kind of calculating a sampling distribution. So the mean of each of those, we do a mean of 71 plus 75 divided by 2, and we get 73, and so on. And so we could calculate each of those means. And then if we plot those, this is actually the sampling distribution for the sample mean from a very tiny population. So I would never actually have you do this for much more than 4 because it just gets out of control. And it's a really tiny sample size from a really tiny population. You can see it already would take a little while if you guys actually had to go through and calculate this. So, we won't do this much, but this is just the idea of what a true sampling distribution is. It's all the possible samples of a given size from that population, and you find some statistic. In this case, they chose sample mean. But we could also do something similar for a sample range. So I'm going to take those same sets of samples, and we could do a distribution of their ranges. And so the range here, 75 minus 71 is 4, and then 72 minus 71 is 1, and so on. And so we plot those potential ranges. And so there's the sampling distribution of ranges. One thing we'll get into the next section is some statistics are good estimates, like in generally the sample mean is a good unbiased estimate of the actual population mean. So if you got the mean of those 4 numbers, the mean of this distribution is about right. Ranges are not very good. The actual range is 7, and notice that only one of our samples actually happened to get the largest and smallest. So while a mean is a good estimator of its parameter, the sample mean is a good estimate of its parameter, range is not. A sample range, like, we have to account for the fact that we're probably not going to get our biggest number and our smallest number. But there's some weird statistics and stuff we can do to try and deal with that. So that's the intro to the idea of the sampling distribution.